Right, I'm going to show you how to answer some combined physics higher paper 1 questions. That's paper 1 if you're doing Edexcel. It's a unit called SP6, but basically it's radioactivity, and all exam boards have got questions to do with radioactivity. You can see there's quite a few marks that have came up on the topic of radioactivity. These questions have been taken from a number of different papers over recent years, so it's quite a popular topic for the examiners to ask you about. Question 1. Medical staff who use radioactive materials need more protection than their patients. Describe some precautions that medical staff could take to ensure their safety from radioactive materials. It's worth 3 marks, so we need to put at least 3 things. Well, if you're going to be around something that's radioactive, try to keep your distance. If you do have to go close to it, just go close to it for a short amount of time. Don't pick it up with your hands, pick it up with tongs. That's those metal scissor type things. Wear a lead apron, because lead will protect you. And monitor your exposure with some kind of radiation badge, like the dosimeter. Basically, the dosimeter badge contains a bit of photographic film, and the longer that you're exposed to the radiation, the darker the photographic film turns. Question 2. Figure 7 is a diagram of 3 atoms. Give reasons why these atoms are isotopes. Well, that's hydrogen, and that's hydrogen. They call this deuterium because it's got a mass of 2, and that's tritium because it's got a mass of 3. What they're looking for is the definition of an isotope. The definition of an isotope is they've all got the same number of protons, 1, 1, 1, or the same atomic number, but they've got a different number of neutrons. That's got 0 neutrons, this one's got 1 neutron, and this one's got 2 neutrons. Question 3. Explain one precaution that is taken in hospitals to limit the risks of exposure to radiation. Well, it's exactly the same as a previous question. Stay away from the radiation as much as you can. Keep your distance. Wear protective clothing. Keep the radiation source in a lead box. Question 4. Everyone is exposed to background radiation. Some of this radiation comes from natural sources. One example of a source of background radiation that does not occur naturally is radiotherapy. State one other source of background radiation that does not occur naturally. So they're looking for man-made sources. Right, you've got X-rays in hospitals, you've got nuclear bomb testing, and you can have radioactive waste. So any of those are man-made, and they'd already said radiotherapy, which is gamma rays in hospitals, but you weren't allowed to say that again. Part 2. Radon gas is a natural source of background radiation. In some parts of the country, a lot of the background radiation comes from radon gas. Explain why there is no radon gas in some other parts of the country. And that's 2 marks. Well, radon gas comes from rocks. And some parts of the country are not very rocky, and some parts of the country will be. For example, the Lake District is very rocky because it's got lots of mountains. Question B. Technetium-99 is one of the radioactive isotopes in nuclear waste. The graph shows the decay curve for technetium-99. So that's the activity in becquerels up the side, and that's the time in years along the bottom. And you can see as the time ticks by, the activity decreases. Part 1. Use the graph to show that the half-life of technetium-99 is about 200,000 years. Well, remember, the half-life is the time that it takes for the activity to half. That's my favourite way of saying it. It is also the time that it takes for the number of radioactive atoms to decay by half. Right, what's that there? That's 1500. 1, 2, 3, 4, 5. Yep, it's exactly halfway between 1400 and 1600. So that's 1500. Right, what's half of 1500? 750. So if that's 600, you've got 1, 2, 3, 4, 5 squares, and that represents 200. So 200 divided by 5 is 40. So each square is 40. I mean, these are horrible axes. Right, we need to get to 750. So that's 600. There's 640, 680, 720. There's 760. So that there. So if we sort of go across there like that, and then come down here like this. The examiners love it when you do that, because it's really easy to see your thought process. And that's your half-life there. And that's what they'd said, prove that it's about 200,000 years. And make sure you say 750. Just so there's no doubt in their mind what you've been up to. Right, part 2. Technetium-99 emits beta particles. Give one reason that beta particles can cause harm to people. Worth 1 mark. It's always the same answer. All of this type of radiation can damage your cells and cause cancer. That's your standard 2 mark answer. They're only after 1 mark, but I still always just put the same thing, and then if it is worth 2, I get both marks. Part C. There are many radioactive isotopes in nuclear waste. Technetium-99 is just one of these isotopes. People are worried about how we should deal with nuclear waste. Explain why it is difficult to deal with nuclear waste safely. Right, well, the problem with nuclear waste is that it's got a long half-life, which means it could stay radioactive for thousands of years. Now, it needs to be stored in big lead-lined boxes or thick concrete boxes. Now, some of these boxes are huge and it's difficult to transport. People are worried in case the boxes will leak. Some people think that terrorists might come and try to get their hands on it to make bombs. If it does leak, it could kill local wildlife. And the leaks could cause cancer in humans. Now, it's only worth 6 marks, so there's quite a lot there. Question 5. Figure 17 shows a Geiger-Müller tube, GM tube, used for measuring radioactivity. That's it there. Describe how a teacher should use a Geiger-Müller tube to compare the count rates from 2 different radioactive rocks. Right, what you would need to do is put the radioactive rock there, one at a time, and let the radiation go into the tube, and that'll tell you how radioactive it is in becquerels, BQ. And you'd basically have to repeat that. Now, when you repeat it the second time with the second rock, you need to make sure that the rock is the same distance away that the first rock was from the Geiger-Müller tube, and you'd have to make sure that it stays there for the same amount of time. And also, you'd have to make sure that you take a reading of this general area when the rocks are not there, so that you can get a reading of the background count. And then you'd have to remember to take the background reading away from the reading when you've got the rock and the background. Now let us show you how to write that down to get 4 marks. There you are, that would nicely get you 6 marks easy. I've saw that question a few times, and it can be tricky for students if you've never saw the question before and you don't know how to phrase it. Question 6. State the name of an instrument that can be used to measure radioactivity. Well, it's just in the last question. GM tube or Geiger counter. It's the same thing. Now remember, all of these questions have been taken from different exam papers. That's why all of these questions are to do with radiation. But you can see, year after year, it's the sort of same questions coming up all the time. So by practicing papers like this, you've got a pretty good idea of what type of questions are going to come up, and you'll do well on your exams. Part 2. State 2 sources of background radiation. Oh, I've had that one before. Do you want man-made or do you want natural? I'll show you both. So natural could be from rocks, could be from food, could be from the sun. And man-made, you've got X-rays from hospitals, you've got gamma rays from hospitals, you've got nuclear bomb testing, you've got radioactive waste. Right, question 7. Figure 8 shows a helium nucleus. 2 of the particles in the helium nucleus are neutrons. State the name of the other 2 particles in the helium nucleus. Well, the only particles that can be in a nucleus are neutrons and protons. So there must be protons. Basic chemistry, that. Question 8. Here are 4 uses of radioactivity. Draw a line from each one of them to the type of radiation it uses. Each type of radiation may be chosen once, more than once, or not at all. Right, sterilisation of medical equipment, that's gamma, because gamma's got so much energy that it kills bacteria and microorganisms. Household fire smoke alarms, that's alpha. Gauge and thickness of cardboard, that's beta. And irradiating food, well, that's gamma as well, for the same reason as before. Gamma's got so much energy, any little viruses, bacteria, microbes will be killed. Question B. Complete the sentence by putting a cross in the box next to your answer. The unit of activity of a radioactive isotope is the becquerel, and that's how to spell it. It's BQ for short. Marie Curie investigated radioactivity over 100 years ago. She often carried radioactive materials in her pocket. Dangerous. She stored them in her desk drawer. Also dangerous. She liked the coloured light they gave off. Mary probably died from exposure to their radiation. Yeah, almost certainly. Part C. Describe 2 precautions that scientists now take when they use radioactive materials. Right, this is the 3rd time I've had a similar question like this. So limit the amount of time that you are next to the source. Keep your distance from the source. If you do have to go close to it, don't handle it, pick it up with tongs or protective gloves. And wear protective clothing like a lead-lined apron. Question 9. An underground oil pipe starts to leak oil. To find the leak, a technician adds a gamma source to the oil flowing in the pipe. Describe how the technician can find the position of the leak. Right, imagine there's the ground. Imagine here's the pipe. Imagine there's the leak. Now, a little bit of gamma can get to the surface through the crack, right? They'd put the gamma into the pipe, right? And the gamma would travel down the pipe. As the gamma's travelling down the pipe, it would be coming out to the surface. So if you get a Geiger counter and stand at the surface, once you get to the leak, more will come out where the leak is. So if you're walking along here with your Geiger counter, it'll have a higher activity once it gets to the crack. Now, how do you say that? Just like this. Use a GM tube, so a Geiger-Müller tube, to detect the gamma. Where the crack is, there will be an increased reading. And that's where you're walking along the top with your GM tube. Part B. Which of these is correct for half-life? Put a cross in the box. Half the time for all the atoms to decay? Nope. It is the time it takes for an atom to half decay. That's an absolute load of rubbish. It is the time it takes for half an atom to decay. That's a load of rubbish. It is the time it takes for half the atoms to decay. Yep. It's also the time taken for the activity to half. As I said before, that's my favourite way of saying it. Question C. The graph shows how the activity of a sample of a radioactive material changes with time. The sample has an initial activity of 80 counts per minute. So at a time of 0, the activity is 80. Use the graph to find the half-life of the material. Right, well, as I just said before, the half-life is the time it takes for the activity to half. So what's half of 80? 40. Right. How long did it take to get down to 40? Near enough 2, sort of just before 2. I'm going to say 2. There's always a range. 2 what? Sausages? No, days. Pay attention to the units. Sometimes they're hours or sometimes they're years. Part 2. Another sample of the material has an initial count rate of 40 counts per minute. Sketch on the same axes the activity of this sample for the first 4 days. Right, so the initial count rate's 40, so that means when the time is nothing, the activity's 40, and they want it for the first 4 days. Right, well, if it's the same sample, that means it's going to have the same half-life. So it's going to half every 2 days. So what's half of 40? 20. Right, so it's going to take 2 days to go down to 20. And then it's going to take another 2 days to half again. So what's half of 20? 10, right? So on 4 days it'll be 10. And then just do a nice smooth curve like that. And they only wanted it for the first 4 days, so you don't need to do the whole lot. D. Some scientists carry out an experiment to measure the radioactivity from a source to be used in a factory. They measure the background radiation before and after their experiment. They take the background count at the same place as they do in their experiment. Explain how this procedure helps to make sure that the results of the experiment are valid. 6 marks. Right, let's take it one at a time. What have they said? So they measure the background rate before and after their experiment. So basically the background radiation can change. So if you measure it before and after and then take averages. And a good thing to say is what background radiation actually is. So background radiation is radiation that is around us all the time. It's random. It depends on the environment. For example, how many rocks are around. It can change over time. Multiple readings should be taken and then an average should be calculated. The background reading should be subtracted from the reading with the source. So what I mean by that is you get the background reading, just say it's 100, and then get the background and the source, and that might be like 1500. So the actual reading from the source would be 1500, take away the 100, which is your 1400. Question 10. Figure 17 shows a Geiger-Muller tube used for measuring radioactivity. Yep, we saw the same picture. So they've used the same picture a couple of times. A hospital uses a radioactive isotope with a half-life of 6 hours. A technician measures a count rate of 80 counts per minute from this isotope. Complete the graph on figure 18 as accurately as possible to show how the count rate from this isotope will change from the time of the first measurement. The first point is already drawn in figure 18, so at a time of 0, it's got a count rate of 80, and they've said the half-life is 6 hours. So that means, remember, that the count rate is going to half every 6 hours. So let's have a look at the graph. I mean, it's a horrible axis again. You've got 10 blocks, mean 5, so each block is a half. So that's 6 hours there. And I want 12 hours. So there's 10, 10 and a half, 11, 11 and a half, 12, and then I want 18 hours, so 15, 15 and a half, 16, 16 and a half, 17, 17 and a half, 18. So after 6 hours it's going to half, so half of 80 is 40, so that's there. Another 6 hours later it's going to half again, so half of 40 is 20, so that's 20 there. And then in another 6 hours, it's going to half again. So half of 20 is 10. And then connect it up. Well, that's rubbish. Use a pencil. So if you make a mistake, that's rubbish. That's better. Use a pencil in an exam, so if you make a mistake, you can rub it out. Right, you'll get 3 marks for that. You'll get marks for the plots and then a mark for a lovely smooth line. Question 11. Americium-241 is a radioactive isotope that emits alpha particles. Americium-241 is used in smoke alarms. Give a reason why it is safe to use Americium-241 in smoke alarms. Right, look, alpha particles only travel a few centimetres in air. And besides, if you've got the smoke alarm, there's the ceiling, there's your smoke alarm there, your alpha will probably be there. It won't even be able to penetrate out of the plastic casing. There will be little holes in the casing, but by the time it's travelled a sort of centimetre, it's not going to really be able to get out. Plus, it's right up on the ceiling, so your head, you'll be walking around down there, so you'll be quite far away from it. So that would get you 2 marks actually. Question 12. What is the approximate size of a hydrogen atom? Right, it's going to be like 0.1 nanometers. Right, well there you are there then. 10 to the minus 10, so that means 1 times 10 to the minus 10, which is equivalent to 0.1 times 10 to the minus 9, which is a nanometer. That's only a millimetre, so that's massive for an atom. And this times 10 to the minus 19 and times 10 to the minus 31, that's too small. So just try to remember that value there. Question 13. Lead-214 is a radioactive isotope. State one way in which radioactive isotopes can be harmful to people. Right, we've had this question before as well. It's always the same answer. It can damage cells and cause cancer. Now sometimes you do have to actually say both of those parts just to get the 1 mark. So I prefer not to say cause cancer. I always double it up and say it can damage cells and cause cancer. It damages the DNA of cells if you want to be more specific, and tie that in with your biology studies. Lead-214 emits beta- particles. Describe what happens to the nucleus of a lead-214 atom when it emits a beta- particle. Okay, so if you've got beta-, it's basically an electron. So it's got a mass of 0 and it's got a charge of -1. Now, the way I like to think about it is because it's negative, you need to pair it up with something that's positive. So what do we know that's positive? Well, a proton. A proton's got a massive 1 and a charge of 1. Now we need to add these things together and we'll be able to tell what particle that the beta came out of. So 0 plus 1 is 1, so this thing's got a massive 1, and -1 plus 1 is 0. So we're looking for something that's got a massive 1 and a charge of nothing. Well, that's a neutron, isn't it? So for 2 marks, we'll say the beta- was emitted when a neutron turned into a proton. I've got nice videos in my SP6 playlist. If there's any of this stuff that's confusing you, make sure you check those videos out. Question 14. Use words from the box to complete the sentences below about ions. Atoms may form positive ions by something electrons. Well, it's by losing electrons. So remember, an atom has no overall charge. It's got the same number of protons, which are positive, and electrons, which are negative. If you suddenly lose electrons, it's going to leave more protons behind than electrons, so it's going to have an overall positive charge. The electrons involved in forming positive ions are it'll be the outer electrons. They are most easily lost. If it did say the atom became negative, that would be because it's gained electrons. Part 2. Which of these radiations is both electromagnetic and ionizing? Well, it's always gamma. Just think about the electromagnetic spectrum, the 7 waves. Is alpha one of them? No. Is beta? No. Is a neutron? No. The only one that is gamma. So gamma is an electromagnetic wave, and it is an ionizing radiation. It's not very ionizing, mind, not compared to alpha and beta, but alpha and beta aren't electromagnetic. Part 3. Which type of radiation will travel the shortest distance in air? Well, that's alpha. Alpha only travels a few centimetres. Beta travels a few metres. Beta plus is the same as well. That's known as a positron. And a gamma is almost infinite. It'll travel an infinite distance until it gets absorbed by something dense, like meters thick of concrete or a few centimetres of lead. That's usually the substances we quote. Question 15. Uranium-238. Right, this is the mass number, by the way, whenever it's quoting these numbers. Uranium-238 is an isotope of uranium. It may undergo either radioactive decay or nuclear fission. A nucleus of uranium-238 is shown as Q in the chart. Look, you'll notice that, yeah, that's the mass number along the bottom, and it's 238. State 2 letters from the chart which show isotopes of the same element. Now remember, the definition of an isotope before was something that has the same number of protons or the same atomic number but a different number of neutrons. So there is the atomic number up the side. So if it's going to be an isotope, it needs to have the same number of protons. So it needs to have the same atomic number. So Q and N are the same. Mind you, look at P and M. P and M also have the same atomic number. So they are also isotopes. Remember, the same atomic number, or same proton number, but a different number of neutrons. So the mass number will be different because if it's got a different number of neutrons. Part B. Explain what happens when Q decays to P. Right. So if Q decays to P, it's basically losing, right? The atomic number is decreasing by 1, it's decreasing by 2. And it also, the mass number decreases by 1, 2, 3, 4. So it's basically releasing an alpha particle. 4, 2, mass of 4, charge of 2. If it was worth 3 marks, we'd get the 3. Part C. Explain what happens when P decays to O. Right, be careful, I nearly said Q there. Right. What happens when P decays to O? So P goes to O. Right. So you can see the mass number stays the same. The atomic number, however, increases by 1. Goes from 90 up to 91. Right, and that'll get you your 2 marks. If it was worth 3, what's basically happened is a neutron, remember, mass of 1, charge of 0, has turned into a proton, right? That's why the atomic numbers increase by 1. So that's a mass of 1, charge of 1. So the mass has stayed the same, look. Mass stays the same. And you get your little beta minus particle, which has got next to no mass, negligible mass because it's an electron. It's got a charge of -1. Remember, these top numbers, when they add together, need to equal that top number on the left, and these bottom numbers, when added together, need to equal that bottom number on the left. Well, they do. If that's just confusing you, though, just stick with the initial explanation. Quite a tricky question, that one, by the way. I've taught A-level physics for 20 years, and that's the kind of questions we used to do at A-level physics. Part D. Particles released during radioactive decay can have different energies. A suitable unit for these energies is mega electron volt. That's A-level physics as well. For one type of decay, the particles released have energies between 4 mega electron volts and 10 mega electron volts. So 4 mega electron volts and 10. The graph shows how far the particles with these energies travel in air. So the distance travelled in air. State the name of this type of particle. Right. Well, what have I said before? You've only got this, whatever it is, it's only travelling like a few centimetres in air. Well, it must be alpha then. It can't be beta because that travels a few metres in air, and it certainly can't be gamma because that travels infinite in air, miles and miles and miles. Part 2. Use information from the graph to describe how the distance travelled in air depends on the energy of the particle. Right. So as the energy has increased, or as the energy increases, the distance travelled increases. All right. Now, it doesn't look perfectly straight to me. It's not perfectly linear. It's a little bit curved, isn't it? Now, I'm not going to start waffling on about that. You could say linear and you might get a mark for it. But look, if it says use information from the graph, make sure that you use information from the graph. Now, I'm just going to use the information from the graph to back up that statement. So I'll just say, for example, when the energy is 4 mega electron volts, it travels 2.5 centimetres. And when it's 10 mega electron volts, it travels, well, just about 10 centimetres in air. Okie dokie. So that's the trigger. As soon as it says use information from the graph, make sure you are actually using the numbers from the graph. Part E. Uranium-238 can only undergo nuclear fission by absorbing fast neutrons. The fission emits neutrons which very quickly lose their energy. Suggest why the fission of uranium-238 does not produce a chain reaction. Well, the first thing is make sure you explain what a chain reaction is. Right, look, let us draw you a picture, right? Just say you've got this big uranium-238. You've got a little neutron that needs to move fast, and it smashes into that, and this uranium atom will turn into 2 smaller atoms, plus you'll end up getting more little neutrons. These little neutrons will then go on to smash other uranium atoms. So these neutrons hitting into other uranium atoms, that actually is the chain reaction. Now what it's saying is you need a fast neutron to split the nucleus. And basically these neutrons here are not fast. They lose their energy quickly. So you're not going to get a chain reaction because of that fact. Right, let us show you how to write it. A chain reaction needs a fast-moving neutron to collide with another uranium atom. These neutrons quickly lose their energy, so won't produce a chain reaction. Right, question 16 is basically the same as question 8a, so I'm not going over that. Question 17 is basically the same as question 9a, so I'm not going over that. And finally, question 18. Figure 8 shows an atom of iron with its electron orbits. So there's the little electrons orbiting around the nucleus. When iron is heated, it glows red. Explain what happens to the electrons during this process. Right, so this was from lesson SP6C called Electron Orbits. I'm not sure if this is on Aqua or any of the international GCSEs, but it's definitely on Edexcel. Right, so basically what happens is these electrons are going to absorb heat energy and they're going to jump up to an excited state and a higher shell. Now, they can't stay in that excited state forever. They're going to drop back down at some point, and as they do, they're going to release a wave of energy, and that energy will be in the form of visible light with a frequency similar to red in this particular example. Right, I'll show you how to write that. Once again, that is pretty A-level-y. That's like a physics A-level question. Right, we're done. So I hope that's helped you. Remember, the more you practice, the better you get. Simple as that. The only students who fail these days are the students who don't take responsibility for themselves. So don't be that guy. Work hard, be nice, and bye for now.